Okay, so we've now gotten the special conformal transformation. There's the finite form of it. We notice that its parameter is an inverse length. It's most clearly written in terms of inversion. So special conformal transformation is achieved by doing inversion, then a translation, and then inversion. So that already gives you quite a bit of information about the special conformal transformation. But now I'd like to develop this a little further and maybe give you a little intuition. So this next bit is really to build up some intuition. Um, and let's proceed as follows. So let's start off again from the conformal killing vector. So this is telling us about an infinitesimal special conformal transformation. So zeta alpha will be equal to x squared b alpha minus 2 b dot x x alpha. And then I'm just going to write this in a suggestive way. So this can be written as x mu b alpha minus x alpha b mu b mu, and this is into x mu. So look at the first term. That's actually x squared b alpha. So this term over here matches that term over there. And now if you look at the second term, this is b dot x x alpha. Well, this is of the form b dot x x alpha, but I've only got one of them on the second term. So I need to add an extra b dot x x alpha. So this also contributes to the red term. Okay, so I've just rewritten this, but this is pretty suggestive, and I tell you why. If you look at this first term sitting here, I've got x mu, but it's dotted into x mu b alpha minus x alpha b mu. So I've got something sitting there. I'm just going to call it alpha mu, and you can see that it is anti-symmetric. So that's what sits inside this bracket. So everything inside that bracket, I have collected and called it x alpha mu, and then I've got an x mu. Well, I'm going to call this effective. The reason why I've called it an omega, it's anti-symmetric, so it looks like I'm doing a Lorentz transformation. But it now looks like I'm doing a local Lorentz transformation because omega depends on x. And then for the second term, I've got minus something multiplied by x alpha. So this looks like an effective scaling times by x alpha. So what this looks like, it looks like a special conformal transformation is doing something like a local Lorentz transformation and a local scaling. Now remember that scalings had a non-trivial effect of rescaling the metric. So we may expect that a special conformal transformation perform a non-trivial scaling of the metric. Well, let's check that. And if you remember, what we had was capital omega was equal to 1 minus little omega. So it makes sense to work out what is little omega equal to and see, this tells us about how the metric is scaled. So let's see what little omega is equal to for this special conformal transformation. Well, it's the usual thing, the divergence of the killing conformal vector, so d alpha, zeta alpha, and then we need to divide by the space-time dimension d. So this will be x alpha, and now let's just put in our x squared b alpha minus 2 b dot x x alpha, and then divided by d. And let's see what we get. When we act on the first term, the d alpha cannot act on the b alpha. B alpha is a constant, so d alpha only acts on x squared. It gives us a 2x alpha. When I differentiate x squared, I get 2x. When I act with the d alpha on the second term, first I could act on the b dot x. That'll give me, oh, sorry. For the first term here, I should also multiply by b alpha minus. Now, when I act on the second term, d alpha could hit the b dot x. It'll give me a b alpha. So I'll get 2b alpha x alpha minus, or it could also act on the x alpha. Now, d alpha x alpha is delta alpha alpha, which sums to give me d. So I'll get a d times by 2d dot x, and this is all divided by d. Similar to what we saw above, these first two terms, they cancel. This is like the statement that when you do a Lorentz transformation, you don't rescale the metric. Those are the first two terms. Those are coming from the local Lorentz. And all we've got left is this second term. And this lands up giving us minus 2b dot x. So indeed, we've got a local rescaling of the volume, a rescaling that depends on x. So this section that we just did now, so let me put it inside a black box. This was more just to try to give you some sort of a mental picture as to what the special conformal transformation is doing, because it is a little unfamiliar. So you can think about it as a local Lorentz transformation and a local scaling. Good. One more thing to do to sew up our discussion of the special conformal transformation, and that is that we want to determine the generator. And by now, I hope the logic is very clear to you. So we start off with the expression for the group element, so the exponential of the Lie algebra element with the parameter, and we let this act on x mu. Then we use the fact that B alpha is infinitesimal, so we can expand this group element and drop the terms of order B squared. So that's what we get. This acts on x mu. And then what should this be equal to? Well, this should be equal to x mu plus the infinitesimal change in x mu, which is given to us by the conformal killing vector, which by now I'm sure you know off by heart. Okay, so I just wrote in what the conformal killing vector was. There it was at the top there. Good. Okay, now, of course, this one here agrees with that x mu sitting over there. So what have we got? Well, I, B alpha, K alpha, x mu should be equal to x squared B mu minus 2 B dot x, x mu. Let me just try to improve my square on the x. Good. Okay, so this is the equation that we will solve to determine the generator. So you've done this many times. I'm just going to tell you what the answer is. It's a little tricky to guess. Maybe you want to pause the video and try. But this is what you should get. Minus ix squared d alpha minus 2 x alpha d, x dotted into the derivative. So let's just check if that's true. So to check if that's true, I'm now going to plug it into the equation that I've just boxed in blue. Okay, so we've got IB alpha. So the I up front multiplied by the minus I in the generator will multiply to 1. So we've got B alpha. Now let's put in the rest of K alpha. We've got x squared d alpha minus 2x alpha. Then this x dot d could be x rho d rho. Just write the indices in. And then this goes into x mu. So let's put the x mu in. There is x mu. Good. Okay. So in the first term, when this d alpha hits the x mu, it's going to produce a delta mu alpha, and that will contract with the b alpha to give us a b mu. So we'll get x squared b mu. Okay, so there was the derivative act on x mu. That's what it does. And then for the second term, we've got minus 2, the b alpha with the x alpha will give us a b dot x, and then x rho d rho on x mu. Well, you might remember that x rho d rho counts the number of x's. Equivalently, d rho on x mu gives you a delta mu rho, And that delta mu rho turns the x rho into an x mu. So this becomes x mu. And if you now look, there is a perfect match between what we got over here and what we have over here. So that's indeed a check that our generator of the special conformal transformation is correct. So we now have all of the Lie algebra elements of the conformal group. So we now have all of the generators of the conformal group. The next thing to do is to calculate the commutators of those generators. So to calculate the Lie algebra of the conformal group.